Today we're going to learn about linear and quadratic functions. Both linear and quadratic functions are part of the polynomial family of functions. If you remember back to probably Algebra 1, polynomials are functions that often have multiple terms, and each term has a different degree or exponent. For example, f of x equals 3x to the power of 4 plus 5x to the power of 3 minus 9x squared plus 5x minus 11 is a polynomial of the degree of 4. So to be a polynomial, we have a couple of rules for our exponents. So in this case, the exponents must be non-negative integers. So the exponents must be non-negative integers. And if you remember, integers are whole numbers. So why don't we want fractions or decimals? Well, think about what happens when you have a fraction for an exponent. So if I had something like x to the 1/2, we know that x to the 1/2 is really the square root of x. So that is going to be a different family of functions. Why don't we want negative? So let's think about if we have x to the -2. If we have x to the -2, that's going to be the fraction 1 over x squared, which is another family of functions. So polynomials are going to have exponents usually, and they must be non-negative integers. Okay, let's look at an example. So which of these are polynomial functions and which are not? So if it's a polynomial function, we'll also state the degree and the leading coefficient. If those are not, we'll talk about why not. So a, which is the function f of x equals 4x cubed minus 5x minus 1/2. So f is a polynomial function of degree 3. So we notice all of the exponents here are positive and they're not fractions. So my first exponent right here is a 3. So we look for the biggest exponent. That's what tells us the degree. So the degree is biggest exponent. And just because I have a fraction in a, that doesn't mean anything because it's not in the exponent. So a is a polynomial function of degree 3. If we look at b, b is not a polynomial function because of this negative exponent. That's going to put that x term in the denominator. So a is, b is not. Now let's look at c. h of x is equal to the square root of 9x to the 4th plus 16x squared. C is not a polynomial because you cannot actually simplify this into a polynomial. If this was a different function, sometimes you can do the square root of different parts and you will get a simplified thing that is a polynomial, but not this time. And d, k of x is equal to 15x minus 2x to the 4th. So k is a polynomial. If you look at the exponents, there's an invisible one there, and there's a 4 here. So this is a polynomial, and its degree is 4. And if we wrote this in standard form, the leading coefficient on d would be a -2. Standard form says that you have to write your functions in descending order of exponents. So this would be written as -2x to the 4th plus 15x. Now let's look at some special cases of polynomial functions. So here are 4 special cases. We have a zero function, a constant function, a linear function, and a quadratic function. So if you look, zero function is basically just f of x equals 0. It is technically a polynomial, but it has a coefficient of 0 and no exponents, so then it ends up being just a 0 by itself. The next one is a constant function. So f of x is equal to a. A is any number that's not 0. Since there is no exponent, that it would be something like f of x equals 5. So it's got a degree of 0 because there is no exponent on a variable here. Our linear function is going to be f of x equals ax plus b. The really important thing to note here is that a cannot be 0. If a was 0, then we would not have the x term, and this would just be a constant function instead. So this is a degree of 1 because remember there's always that invisible imaginary exponent of 1 there. Quadratic function is going to be ax squared plus bx plus c, and again a is not equal to 0. We don't want to get rid of our term that has the exponent of 2 because a quadratic function must be a degree of 2. I can get rid of the bx term, I could get rid of the c term, and I would still have a quadratic function. But without the x squared term, I would not have a quadratic function. Now let's look at linear functions. A linear function is a polynomial function of degree 1. That means that the largest exponent is a 1. So it's got this form. It's going to look like f of x equals ax plus b, where a and b are constants. And a is not equal to 0. So it's important to note that a linear function will give you a graph of a line, but not all lines are linear functions. So the ones that we need to watch out for are vertical lines. Those fail the vertical line test. And then horizontal lines. Horizontal lines are actually graphs of the constant function. And so we can say that a linear function is only lines that are slanted, so they're neither horizontal nor vertical. So now let's talk about slope, rate of change, and average rate of change. So slope, we remember. Slope has the formula. We usually call slope m, and we almost always say slope is rise over run. We have another formula that says y2 minus y1 over x2 minus x1. And the way we often say that is change in y over change in x. So we abbreviate that as delta, the Greek letter. So delta y over delta x. So we are going to mostly work with delta y, delta x, change of y over change of x. We're also going to work with something called average rate of change. Our formula for the average rate of change would be, if we have a function y equals f of x, and we are going to be looking at the interval between x equals a and x equals b, and we know that a cannot be equal to b, otherwise we wouldn't have an interval to work with. So our formula for this is f of b minus f of a divided by b minus a. So the top part, we are plugging the values of b and a into our function and calculating that out. So this is going to be very similar to our slope because this is how does the function change, and that is going to be our output, which is our y, and then the bottom is our input, which is our x's. So something to note for average rate of change, if it's a linear function, it has a constant average rate of change. So we just call it rate of change. We don't worry about the average part when we're talking about linear functions. When we think about other functions that have different shapes than a line, we know that their slope changes as it goes around. So it can have an average rate of change that is not constant. Okay, next let's talk about linear correlation and modeling with lines. So to find linear correlation, we generally take a set of data first and we put it on a graph in a scatter plot. So here are 5 scatter plots, and we're going to look at the different types of linear correlation that they have. So if we are looking over here at this first graph, we say that its description is a strong positive linear correlation. If you look at all of the dots in this, they are very close to a straight line, but they're not perfect because real-world data is never perfect. If we look at this second graph right here, it says this is a weak positive linear correlation. So the positive part of these two descriptions refers to a positive slope. It is increasing, the y's are increasing as the x's increase. So the second one is weak because if I tried to draw a line, it doesn't really actually come all that close to about half of the points. Some of the points are kind of close, and the rest are kind of just spread out. So it is not a very strong correlation. Looking at this third graph right here, it says little or no linear correlation. If I tried to draw a line anywhere through this data, it wouldn't make sense because it's so spread out. So there's little or no linear correlation. So you can see this circle is closer to a circle on this one. This one's a pretty stretched out oval, and this one's even skinnier and more stretched out. If we look at this fourth one, it says it's a strong negative linear correlation. So you can see again, if I draw a line, I can draw a line kind of through that data, and it would be close to most of the points. So it is a strong negative for the slope correlation. And looking at this last one, it says it's a weak negative linear correlation because negative slope, but it doesn't actually end up tightly clustered along the line. So we've come up with something called a linear coefficient. We call this R. And the linear coefficient R helps us to describe what type of relationship the data has. So the coefficient is going to be between a -1 and a +1. So when it is greater than 0, it's got a positive linear correlation. When it is less than 0, it's a negative linear correlation. The closer that R gets to being 1, positive or negative, the stronger correlation it has. So number 4 says when the absolute value is approximately 1, there's a strong linear correlation. So the closer that number gets to 1, the stronger the correlation is. When it is closer to 0, it's weak or no linear correlation. We're also going to be doing a bunch of regression analysis. We've done this a couple of times in the past. So let's write down some steps so that we can remember what it is we're supposed to be doing when I ask for a regression analysis. So first step is to enter and plot the data. This is done in your graphing calculator, and if you need help with lists, let me know. Then you'll find the regression model that fits the problem or situation. So you'll need to be able to decide, is it linear, is it quadratic, is it something else, and then figure out how to apply that. Then you'll superimpose the graph of the regression model on the scatter plot. So we're going to be graphing both the regression model and the data that you plotted. And you're going to check the fit. If it is a good fit, you'll see it. If it's not, it'll be more like our little or no linear correlation, or it just won't even fit into the data. So use the regression model to make predictions called for in the problem.